Is that how you supposed? Okay. So, it's working. Okay, so like what we're interested in, I'm not going to talk about entanglement right away, I'll get to it. But what we're basically interested in physics is the dynamics of systems. You hear a lot of talking about like ground state wave functions and things like that. But the more interesting thing really is dynamics. Because like when you do an experiment, for example, you usually see like something dynamical. Like if you do neutron scattering, you excite particles and they fly around and do something. So like the really interesting thing is dynamics. Now, the reason why people are interested in ground states is because the ground states sort of let you predict something about the dynamics. And so, for example, if you study something like a solid, if you have a solid material, it's rigid. And that's something about the dynamics. Like if I take the chalk and try to bend it, I see that it doesn't bend. And the neat thing about that is that that's related. It's surprising. You wouldn't think that's related to something static about it. But if you look at the chalk microscopically, you see that like the particles in the chalk are arranged in a periodic lattice. Actually, I don't know if chalk is so regular, but probably it is. It's calcium something. So must be a crystal. So when you see a regular arrangement in the ground state, that means the response to a bending will be very small. And if you see a random arrangement of particles, then you usually have some more fluid behavior. So there's a connection between the ground state behavior and the dynamics, which seems really surprising, because you would think if you just know what the system's doing when it's at rest, how would that tell you any information about the excited state behavior? So there's examples of this beyond, like this example is sort of related to symmetry breaking. And in quantum systems, it's like kind of more like a bigger variety of examples. So one example is this principle that if a system has long-range correlations in the ground state, then there's no gap. And a more physical way to say that there's no gap is to say that it has a good thermal conductivity. Like a power, let's just say it has a thermal conductivity at low temperatures. And also a heat capacity that's a power law instead of being exponentially small. So that's the relationship between the very ground state. All you have to know is the ground state wave function has correlations of all the parameters, all the variables that go exponentially. If that's true, that implies that there's excited states with very low energies. Yeah. Yeah, so that's at first, when you hear something like that, you say that just can't be possible. Because the ground state is just one wave function. So you could take any ground state and any excited states and put them together. Because if I just suppose this is the ground state. And then I can just take random other wave functions that span the Hilbert space. And then I can make a Hamiltonian with any energy levels that you like to have by just combining those together. So if you make these energies bigger than this one by a certain amount, then there'll be a gap. So like the ground state wave function really can't tell you anything about the excited states in general. But the thing is, physical systems have local interactions, like you said. And if you assume that there's local interactions, then this is true. That's the theorem that Matt Hastings proved. So Matt Hastings proved that for local interactions, how did I say it?
Yeah, I don't understand how this.
Wait, I said it backwards, actually. No, wait. I said it confusingly. I said it wrongly.
There's a long correlation line.
I said it's a long correlation line. So if it's a power law, then the excited states have a low energy. Or the other way to say it is, if there's a gap, then the correlations are exponentially decaying, the converse statement.
But as it gets longer and longer range, the correlation length grows, and so the gap will...
Yeah, if you have the precise version of Hastings' theorem says, the smaller, if you look at the ratio of the gap to the size of the interactions, the smaller that ratio can be, the longer the correlation length can be. So for local interactions, gap implies exponentially decaying correlations. Another neat example, a sort of special case of this theorem, is an old way of classifying metals and insulators, which I think is from Kohn made it realize this. That in an insulating material, just like an insulator, the density has exponentially decaying correlations. And in a metal, the density has Friedel oscillations, which decay. They oscillate and they decay like a power law, like something like this. I don't know the power.
Does that theorem go backwards also?
It doesn't. It's sort of I think in practice it goes backward, but it doesn't have to. Like a simple example is if you have a ferromagnet, there's no long-range correlations. I mean, there's infinite range correlations, but there's no power law. The fluctuations have no correlations.
What I meant is if we have an exponentially decaying correlation, is that actually good?
Yeah, so if you have a ferromagnet, there's no fluctuation, so there's no correlations. So it's like infinitely fast decaying correlations, but it's gapless. But that's I think basically practically the converse is also true. Yeah. I don't know. I think so, but I'm not sure. I can say then the way I understand the proof intuitively is that you can find the ground state of a system by starting with a product state, where like each particle is in its own state, and then evolve it in imaginary time, which will get it to decay to the ground state. If there's a gap, it'll decay pretty fast to the ground state. But in a given length of time, correlations can only propagate a certain distance. So you get close to the ground state without having enough time to get a long-range correlation. And this involves there's this Lieb-Robinson bound which tells you how fast correlations can grow in time. So that's how you prove it, I think. Do you have a question?
Yeah, the power law in the density.
Yeah. Yeah.
This is not result.
Is that right? Or okay.
I mean, this is the power.
Okay. Yeah, I just I'm not even sure. Yeah. Yeah. Yeah, so I mean, this might be wrong. I just put a power because I wanted to put a power. I mean, I know it's some power, but I don't know if I got the right one. It means like in the Hamiltonian, you have interactions between like spins or between density that has a finite range. I think, well, the way I'm thinking, let's just to be precise, let's just say fixed finite range, like not even exponential. But I think it's also true if it's exponentially decaying range. It can't be a power law decaying range because then you'll automatically have a power law correlation just from through the interactions themselves. Is there another question? I thought okay. Wait, when did it start? When did I start talking?
You start at 3:45. You go till 5:15.
Okay. So I'm going to try to divide the talk up into at least 2 talks. So I'm going to try to end the first talk in half an hour. Just so. So that's a neat thing that you have this. And one way to think about why this theorem is true is that in the ground state, if you have long-range correlations, it's because there's low energy excitations, and they're excited by virtual processes. And so you have these sort of long wavelength excitations that are spread out over an area. So anything, like if you have a particle if you have like a superposition of waves that are spread out over big distances, then a particle over here will be correlated to a particle over here because they're both kind of fluctuating with the same wavelength mode. So this result is related to zero-point motion. And so the question is, what do we really mean by zero-point motion when you only have like one state? Like, what does it mean to say that in the ground state you can see some evidence of excited states mixed in? And what I'm going to show you is how to use entanglement to like make a precise definition of what zero-point motion is. So this theorem sort of reflects zero-point motion. And you can make the idea of zero-point motion sort of more precise by looking at entanglement. So I'm going to just, okay, so entanglement is this thing that, for example, Einstein and Podolsky and Rosen noticed. They looked at, well, they didn't look at this, but this is analogous to what they looked at. And I'm going to give some articles that you can read, and one of them is the original paper by them. And it's a really, really neat paper, I think, because it's like a magic trick. They like set you up to expect something, and then they say, and this is what actually happened, and then you realize how amazing quantum mechanics is. So to make them look better, I'm going to do a not so good job of explaining it. So I'll do the sort of regular way people say it. So if you look at the state, if you measure the state of the first particle, if you measure the SZ for the first particle, and you measure, so you have two electrons in this state, and then you share them between, like me and someone else in Cincinnati, for example. And so you'd think that, like, there can't be any correlation. Like, if I change the state of my particle, it can't change the state of their particle because they're so far away. So, but if I measure SZ in my particle and I find it's up, that means that this part of the wave function doesn't mean anything. And so their particle has to be down. So if I measure SZ is up, the other person has to measure their SZ is down. And vice versa. So that doesn't actually imply that I affect, well, if you think about this as a quantum mechanical state, it really sounds like I affected the state of the particle, of their particle. Because originally, before I did the measurement, it had a potential to be up or down. And after my measurement, it only had a potential to be the opposite of what I measured. But I don't know what a potential means. Is that really a physical thing? The idea of a potential for something to have different values. Because until you measure it, you don't know what happens. And like a correlation like this, you could have in a classical way. So an example is if you go to the store and it's like the end of the day and there's only or let's say you go to the C4C and it's the end of the day and there's only a cheesecake and a chocolate brownie left. And if I get the cheesecake and two people left and one person gets the cheesecake, then the other gets the chocolate brownie. And and then someone else who had seen that there were two left and he sees that I got the cheesecake, he knows the other person had the chocolate brownie without having to look at it. So it's not amazing, really, that this happened. What? Oh, yeah, I could take both. But, so this isn't so amazing as a classical thing. But what is amazing is if you look at the SX, if I measure SX and I see it's pointing to the right, for example, then you might be then the SX of this person is always pointing in the opposite direction. If this is pointing to the right, then that's pointing to the left. And you can see that by writing the up state in terms of the left and the right basis. If I plug that in to this wave function, then I'll get then I will get the same state back with up times right times left minus left times right. So if Sx is right, then the other Sx is left. And the way that works out is and that seems kind of strange because you could say, well, potentially I could have measured Sz instead of Sx. And if I were to measure Sz, the wave function would have ended up either this term or this term. But if it's either this term or this term, the second spin is either down or up. And down and up each have 50% chance of being right or left. And so it really should be 50-50 chance of pointing right or left because I could have measured Sz instead of Sx. And since he's far away, he can't know what I'm going to measure. So that's why it seems very strange. Yeah. So actually what he can't actually tell what I did. Because if I measured Because if I measure at z, he has a 50-50 chance to get up or down. Even though his is perfectly correlated to mine, if he doesn't ask me what I measured, he would never know that. So it does, as far as he knows, he gets the same answer whatever I measure. It's only the correlations that are strange. So this is something that Bell made more precise with the Bell inequalities, where he showed that it's actually, like, for just this first line, there's this simple thing with the cheesecake and the chocolate cake that you can show that this could happen classically. And actually, if you put these two things together, you can actually explain it classically too. And what Bell showed is that if you measure a third direction also, it becomes impossible to have a classical explanation of this. So like the simple classical explanation of this phenomenon is that each electron has like two things inside of it. One is the SZ thing and one is the SX thing. So like you could say one is the dessert and one's the salad or something. And the desserts are opposite and the salads are opposite, and there's nothing strange about that. And if one person measures the dessert and one measures the salad, they're uncorrelated, and there's nothing strange about that. But once you get to three different things, there's no way to. Then there are correlations between different pairs, like the dessert would be correlated to the side vegetable, and that correlation. So you have three things basically. The idea of Bell's inequality is that this thing is correlated to this thing. Well, anyway, you can read about it. It's kind of hard to explain it without actually explaining it. But I'll give you as an exercise a fancier version of Bell's inequality, which is very nice. If you look at this state, this involves three particles. This is called the Ghz state. And what you do is you say, suppose, so you have three people which each have one of the spins. And you suppose that they each measure either the Sx or the Sy component of the spin. And wait, let me just make sure I can. So I think what happened, let me think. So if two people measure, what you should show is if two measure Sy and one measures Sx, then an odd number of them, so either one or three people, then an odd number of people get -1. And on the other hand, if the people measure, if all three measure Sx, then an even number get 1. So first try to show that this is true, and then try to see why this couldn't happen classically. So what I mean by that is, since there's a perfect correlation like this rule, there's a perfect correlation. Like if you know the outcome of two people's measurements, you know the third person's measurement. So if this happened in a classical system, the only way that would be possible is if the values of Sx and Sy were all predetermined. Because if there were any randomness in Sx, it couldn't be so perfectly correlated to the other two spins. So they have to be predetermined. I mean, maybe they're not predetermined before you set up the state, but once you distribute them to the person. They're predetermined, which means Sy and Sx both have a well-defined value. So if you can think about this and see why, if Sy and Sx have well-defined values, this is impossible. Of course, we know quantum mechanically that Sy and Sx shouldn't have well-defined values, but here's a real proof that they really can't. Okay, so now I'm going to define this. So this thing is called an entangled state because the one particle, like if you look at the first particle, you don't really know what its state is until you compare it to the second particle. Like the interesting thing about that state is the relationship between the two particles. If you look at the first particle, it could be either up or down with 50-50 chance, and it could be either left or right with 50-50 chance. There's nothing special about it. But there's this really strong relation to the second particle. And that's called entanglement. So what I want to say is, like, how can you define entanglement instead of just looking at it and say that looks unusual, so it must be entangled, or waiting for someone like Bell to come up with a clever inequality that shows it's entangled. So what I'm going to do is so the definition of entanglement is I'm going to take a system with two parts, which could be two particles, or they could be just like two whole crystals or whatever. Just a system with two parts. A and B. And I'll take the wave function for the whole system together and write it as a sum of wave functions for one part times wave functions for another part. So if you just have like two systems and you prepare one and you prepare the other one separately, then the wave function of the whole system is whatever the state of the first is times whatever the state of the second is. But if there's entanglement, then you sum several terms like this, and that leads to correlations. So my first definition of entanglement, which is going to not be exactly right, but we'll fix it in a second, is that if there's more than one term in the sum, then the system is entangled. So let's see if that makes sense. So this is a good example. That's entangled, and there's more than one term. You can write it in this form with two terms. Here's another example, though, which is one I'm worried about. So if I take So is that, normalize it by multiply by half. Is that an entangled state? Why not? Yeah, so you can factor it, or you can change to a different basis where it becomes a product state. So like if I look at it here, it looks like it has this form of So, well, I didn't say yet what these I's can be. They're just any states. Yeah, these I's, this I, sorry. So this is a sum over a sequence of states, and the IA doesn't have to be the same state as IB. Well, it's a single sum with one variable, but the states don't have to be related. Oh, yeah. Well, yeah. So, but I didn't say that the different I's have to be different from each other. So I could say like, call this one both 1, like call this both 1 and 4, the upspin. But that's I've got to improve. That's how I have to improve on it. So the problem with this, so this wave function looks like a sum of a bunch of terms, but I can just factor it out. Like if I factor out up, then it's multiplied by, I just combine together the ups, and that's multiplied by up minus down. And if I factor out down, it's also multiplied by up minus down. So this is just equal to up plus down times up minus down. So this one just factors. So it may look entangled in one basis, but not be in another basis. And the problem is basically, I can't, in this case there was an entanglement, because if I know the first spin is up, then I know the second spin is down. But in this case, if I know the first spin is up, I have two terms, so I don't know what the second spin is. So this, just having something like this doesn't mean you have an entanglement. So to make it correct, it's not just more correct, I will just add another statement. Where each of these set of wave functions is an orthonormal set. So if these are orthogonal states, that means some clever experimental measurement can distinguish between them. It might have to be really complicated, but there's some way to distinguish between orthogonal states. So then, if I know the first system is in state I, first part is in state I, then I know the second part is in that same state, because, or another way to say it is, if I know the first one is in state I, then I know the second one isn't in any of the other states except for I, because the other states are all orthogonal to this state. So that's why you want them to be orthogonal, to really define this to be to define entanglement based on this. Mm-hmm. Yeah. Yeah. So I guess if the I's weren't orthogonal, I couldn't even measure which state A was in, because all those different states aren't orthogonal to each other. So I couldn't, if one term was up and one was right, if I measure it's up, it might mean that it was actually right, but then it collapsed to be up.
I guess I'm just looking at the product state that you wrote out. So where's that y?
Like this, if I look at this term and this term. Oh, in the product state itself, it's fine. Oh, the first way I look at. Yeah. So this term and this term aren't orthogonal to each other, because they're both ups. So each term, both factors. Yeah, each A part, are each orthogonal to each other. So let's see. Yeah.
Are you assuming both A and B are same dimension?
If they're not the same dimension, then there will be some parts, some states that are just not included in the sum. Like if one has a bigger dimension, then there'll just be some states that it just can't be in. So I didn't say I has to be a basis. It could just be a basis for a subset of the space. That's what happens if one's a bigger dimension. Yeah.
Why can't we in general turn that
You say why can't we do that?
Yeah, why are
Well, you could always do that, but that doesn't mean there's entanglement. You only know there's entanglement if it has this form, where there are orthonormal states. But there's so that's sort of related to an important question, which is how do you even know you can do this? Because if I just take a general wave function and I expand it, I factor out sort of like I did here. I take up and see what it's multiplied by, and I take down and see what it's multiplied by. Then I'll get something like this. And the first part will be orthogonal because the two terms are up and down, which are orthogonal. But the second one may not be orthogonal to each other. So it might seem like you can't always do this, and then you wouldn't, if you couldn't do this, you wouldn't be able to figure out whether something's entangled or not. So let me show you why you can do this. This is the linear algebra part of the lecture. So like what you just said, if I just start with the obvious, just like choose some basis for each state, which could be up and down, or if it's more dimension, I just, whatever, I take a variable that describes the whole Hilbert space. Then I can take a wave function and write it in the form lambda AB times A for A and B for B. So where A and B are, these states are spanning the Hilbert space into some basis, like maybe the eigenvalues of SE. So now I'm going to take this lambda, and I'm going to think of that as a matrix. Let me just assume they're the same dimension for now. And I'm going to take that lambda, and I'm going to write it. I'm going to use something called the singular value decomposition, which says you can take any matrix and write it as a unitary matrix times a diagonal matrix of positive numbers times another unitary matrix. Actually, I don't want to call that lambda because I'm going to use lambda. I'm going to call d lambda, actually. Let me just call this like r. No. I call it r. So I can write any matrix in this form where these d's are positive or zero numbers, and they're real numbers. So you might, I think this is a kind of surprising thing because you're used to saying you need a Hermitian matrix to be able to diagonalize. You need something to be Hermitian to be able to diagonalize it. But in this case, we're allowed to have two different unitary matrices on the same side, and then it's possible to diagonalize any matrix in the sense.
Is there a geometrical interpretation of the way we have at least orthogonal measures? It's a symmetric interpretation. Choosing
Yeah. Well, I think it's like if you're mapping one space to another space, and in the process you're sort of contracting it in perpendicular directions and rotating it at the same time. I think that's what it says. Yeah, where the di's are greater than or equal to 0. You don't have to assume that, but if you don't assume that, it just makes it more unique. Like the di's wouldn't be unique if I didn't assume that. So I'm not going to prove it, except that probably later on I'll sort of prove it backwards by physical interpretation of it. But let's just assume this, and then I'll just plug this into that equation for psi and see what it says. So if I just plug in r is u dv, let's see what I get, but let me write u dv out as the sum over indices. So I have uai di times vib. That's the value of rab. And then I sum that over ab, and then multiply it by. I just substituted r equals u dv into the equation for psi. But now I can just take the sum of a and b on the inside and just combine the uai with a. So I get sum of A, sum over A, UAI. And I'll combine the V with the B. And then I have the DI in front here. And then if I just call this state, like this superposition of A's, I'm just going to call that the state I, because it depends on I. And I'll call this state I sub IB. And the different I's are orthogonal to each other, which you can check. Like if I was just, like, because these U's are columns of a unitary matrix, and the columns of a unitary matrix are orthogonal to each other. So then so that gives that expression for psi, which is called the Schmidt decomposition. Okay, that's that. So, yeah. So then you can tell whether a state's entangled or not by just checking how many terms, is there one term or are there more terms in the Schmidt decomposition. And the physical interpretation of DIs is that they're the probabilities, or the square roots of the probabilities for getting a different each state. So like if I measure the state A, if I measure whether system A is in state I equals 1 or I equals 2 or I equals 3, I'll get some answer. And the probability for a given answer is just the square of that coefficient, which I'll call P. So if the state is entangled, there's a certain probability distribution for the state of part A of the system. And it's actually the same probability distribution as for the state of part B. So both parts, when two parts are entangled, each part has the same like statistical distribution of possible states. And those statistical distributions are perfectly correlated to each other. Yeah. Well, if there's a phase, I can just take the phase and factor it into IA or IB. That's why I assumed it was positive. Okay, that's the end of my first talk. I'm trying to get 4 talks, so I'm dividing it up into 4 45-minute talks. So is there any questions?
So is there a connection between the beginning of this talk?
Well, it was, no, not yet. That's what the second talk is about. Yeah, so this is, I said that in a metal, for example, or in any gapless system, you have long-range correlations in the ground state. And those correlations are sort of a special case of entanglement. Like when two systems are entangled, they're correlated to each other.
So you should say if there's no entanglement, you just get 1.
Yeah. Yeah. There's no standard, like people have a lot of different definitions of it, but there's not any standard like definition. So one thing you can try to show is, or try to find an example with 3 particles where you can't decompose it like a Schmidt decomposition. Like it's not, for some states it's just not possible to write it as a sum of terms which are each orthogonal to each other. I think people have measures, but I don't really know. I don't know much about it. Like, there's things like, you could say like 2 parts of it are entangled with each of the 2 parts are entangled with each other, but then you would also want to be able to define what entanglement is between all 3, but you can't see it with 2. Like in that state over there, if you ignore the 3rd spin, there's no correlation, no. Yeah, if you ignore the third spin, the first two spins are obviously correlated because they're both up or both down. But there's no quantum entanglement between them. Like you can't, if you don't look at the third spin, you don't see any funny thing like Ghz inequality between the first two. So that thing has only 3-particle entanglement and no 2-particle entanglement. But I can say that, but I don't have any like precise definition of what that means.
There was some statement about monogamy.
Yeah, like this type of entanglement, you can show if two particles are perfectly entangled, like in the Einstein-Podolsky-Rosen paradox, then those particles, neither of them can be entangled with the third particle.
You think that by this measure, there's no such thing as 3-particle.
Yeah.
But there may be some other measure.
Yeah. So, I mean, this is sort of an example of the monogamy of entanglement. I started with 2 particles, and then I tried to entangle them with a third particle also. And then the first 2 particles aren't entangled anymore. So there's a classical correlation. There's a correlation between the SZs, but there isn't any correlation between the SXs anymore once you put the third.
Could you explain what's like say, let's say you split a system, you split it.
Mm-hmm.
So it has the same dimension.
Yeah.
So that really
No, yeah, they may be just completely different states. They just have the index. There's the same number of states in both. And I'm labeling the ones that are correlated to each other are the ones I give the same label to.
I mean, they're distinct because U and V are different. So with two different linear combinations. Huh?
So U and V is the property.
I guess I'm just saying, IA is a linear combination of little a, capital A, and it's one type of linear combination. You still label by I because the I is diagonal.
Yeah.
But the other one, the D linear combination of state.
Yeah.
And so then there are two different.
Yeah. If you had some symmetry, they might be related to it, but.
Label them by the same thing just because they're where they appear diagonal.
Yeah. Mm-hmm. Well, from this formula, you just take 2 different A's and take the overlap, and you'll end up, the expression you get will end up being part of the definition of U being a unitary matrix. So that's where it follows from the U being unitary. So maybe I'll go to start explaining how the physical meaning of this entanglement. So I want to what I was saying is that entanglement is related. That these correlations that you see in a ground state are sort of like 0-point fluctuations, and I want to say what I mean by that. So it's like if you're looking at the ground state of a system, it's a definite wave function. There's not any uncertainty of it. Unlike at a finite temperature, you have a Boltzmann distribution for all the different states. But in the ground state, there's only one wave function. So what does it mean to talk about 0-point fluctuations if you have only one wave function? And the answer I can see by starting from the Schmidt decomposition. So what I'm going to talk about is like the idea of the what people call the Entanglement Hamiltonian, which is that if you look at a part of a system, it seems to be at a finite temperature. Like it seems to be the Boltzmann distribution for some Hamiltonian at a finite temperature. So if you look at the whole system, it's in a definite state. But if you look at a part of it, it looks like it's in a thermal state. So you can already see that from the Einstein-Podolsky-Rosen paradox. Because if you looked at just one of the two spins, it just looks completely unpolarized. It has a 50-50 chance to be in any direction of, whichever component of the spin you measure, it has 50% chance to be in either direction. And it's only the correlations between the two spins that are well defined. So if you wanted to say that in a kind of precise way, you could say that wave function is the eigenfunction of Sxa times Sxb, and Sya, Syb is the eigenfunction of both of these, but it's not an eigenfunction of the single variables. Because this one anti-commutes with that. So if it's an eigenfunction of this, it can't be an eigenfunction of this at the same time because they don't commute. So this system is defined by the relationship between the two spins, not by the state of the two spins separately. So I want to sort of generalize this idea that the part of a system can be in a mixed state or in an uncertain state, even though the whole system is in a definite state. And the way I'm going to do it is by defining the reduced density matrix of part A of the system. The way I do that is I'll take the wave function for the whole state and do the partial trace. And what that means is I take psi AB for this and psi AB star. This represents this density matrix. And then I'm going to set B equal to B prime, as you do when you take the trace and sum over it. So that's the definition of the reduced density matrix. And the reason that's a good definition is because before I say that, if I calculate this for this Schmidt decomposition, so take a general entangled state, which I can write as the square root of these probabilities. Now if I take this Schmidt decomposition, these psi's are diagonal. So for each A, I only have to sum. I'll let A go over this basis and B go over this basis. And because the psi's are diagonal, well, let me just write it out. That's easier. So the psi is equal to But now I'm going to set the state of part B of the system to be the same in both the bra and the ket. So I set I equals to J. And then that means that that means that this I has to equal that J also. So I end up with that as a density matrix. So what that is it's just like a classical mixture of different states. It says that this system can be either in I equals 1 with probability P1 or I equals 2 with probability P2 or so on. Yeah. Well, this is sort of one way to define what you mean by 0-point motion. So it might not exactly correspond to intuition about zero-point motion. But like the example you just said, you can think about if you have a particle that's like in the ground state of a harmonic oscillator, so it's spread out a little bit. There is an entanglement of space. Like there's not an entanglement between two different particles because it's not two different particles. But if I have this Gaussian wave function, and then I look at these two parts of space, and I measure each part. If I find the particle over here, then I won't find it over here. And if I find it over here, then I won't find it over here. And whereas if you have a delta function, you don't have that kind of entanglement. So it's kind of a silly thing, but that's the relationship between the ordinary way of thinking about zero-point motion and what I'm talking about. I'm talking more about like if you have a magnetic system with spins. So then you have like one spin is entangled with another, means that sort of one spin is oscillating, it's causing the other spin to oscillate in a way that's correlated to it. That's true. Yeah, so this actually is almost the opposite of the standard definition of zero-point. Yeah.
So that psi is really the R, and so then really, once we think about density matrix, really just that R.
Yeah.
And now it's not symmetric.
Yeah. So that's the way you can actually prove the singular value decomposition. Is you look at the end of this and you see that the density matrix is diagonal in this basis. So you could have done it in the first place, just diagonalize the density matrix, and then you can go back and prove that automatically. That gives you the states of system A. And then you can figure out what states of system B correspond to them and show that they're automatically orthogonal to each other. So the reason for calling this a reduced density matrix, the reason for looking at this thing is that if I want to know the expectation value of any operator of part A of the system, it only depends on that reduced density matrix. Sorry, this is wrong way. So if I want to know the expectation value of O in the state, where O is an operator on part A of the system, you may think like because they're entangled, I can't figure out the expectation value of OA without knowing what state B is in. But all you need to know is the density matrix of part A. You don't need to know the details of this part B. You just have to know the density matrix of part A. And then you can find the expectation value of OA by doing this. This is something that I was very excited about when I learned this, because I always thought, this idea that quantum mechanical systems are very complicated because you have many particles and you have to know the wave function for every combination of spin up and spin down of each particle. So you have if you don't have a non-interacting system that you can reduce to single particles, it's really complicated to solve many body systems. But on the other hand, you intuitively feel like it shouldn't be that complicated, because if you just look at this part of the system, it shouldn't be affected that much by something really far away. So you should be able to do a little bit at a time. But because you have entanglement, you can't define what state is this part of the system in, because it's entangled with the other part. So you can't even say, I figured out. You might say, well, you don't worry about finding the whole system. Just find out the state of this part of the system. But that doesn't even mean anything because it's entangled. But actually, if you just look at the reduced density matrix of this part of the system, that does tell you anything you want to know about that part of the system. But statistical, and it doesn't give you all the correlations with the rest of the system. So that's a nice concept of the idea of using density matrices rather than wave functions. Lets you look at parts of systems. So anyway, what I just showed a sort of interesting duality that happens in a classical system, which is that if you have a definite state and there's correlations between different parts of that system. I don't know if I said a classical system. Did I say a classical system? This is something that happens in a quantum mechanical system. It's very special to quantum mechanics. So if I have a system in a definite state, and there's any uncertainty in one part of the system, that part of the system, that uncertainty has to be correlated to the other part of the system. So so any uncertainty in this part implies uncertainty in that, assuming that the system as a whole is in a definite state. So let me just write sort of some equations for that. So if you look at the entropy of the system as a whole, if it's in a definite state, that means the entropy of the system as a whole, which I'll write SAB. So that means the S of both parts combined together. That's equal to 0. But even if this is true, we just found that parts of the system can be in indefinite states. But the interesting thing is if I calculate the density matrix for B, it would be exactly the same form. It would have exactly the same probabilities, just the different states in it. So if there's any uncertainty in part A of the system, then there's exactly the same uncertainty in part B of the system. So entropy of two parts of the system are always equal. Is that true in a class? If this isn't true, like at a finite temperature, would the entropies of two parts of the system have to equal each other? Can someone think of an example where it's not true in a finite temperature system? Or maybe any example you think of. Yeah. Yeah. What did you say? Yeah. Yeah. If you have like a gas and you split it in two parts, the entropy is proportional to the volume of the two parts. So the big part would have a bigger entropy than the small part. But in the zero temperature, the entropies of the two parts are equal to each other. So that's a neat effect in the quantum mechanics. Okay, and so I'm going to use this to define entanglement. I'm going to say that the entanglement between A and B is just the entropy of one of the two parts. I'm going to define entanglement to be SA or SB. Well, let's suppose there's a unique ground state for now. I think if it's not unique, we're going to choose one of them and talk about the entanglement of that one. That's something we can talk about for topological, where it's actually interesting to think about what happens for the different ground states. Okay, oh yeah, so let me define the entropy. Here we have a statistical distribution, and if they're all equally likely, the usual definition for Boltzmann is to just take the log of the number of states. But if they're not equally likely, then you should sort of count, like if there's a big peak where the probabilities are larger, you want to just sort of count the number of ones where the probability is as large as it's the largest. So the way you do that, a formula that agrees with like thermodynamics definition, is the entropy is the sum of p times log of 1 over p. So you can check if they're all equally, if all pi's are equal to one another, then this just gives you the log of the number of terms. There's other definitions. There's something called the Renyi entropy, which is a variation on that. But this is the one that agrees with statistical mechanics. So, well, that's the way people originally understood the area law. Yeah, I mean, I kind of, well, let me just, I'll talk about the area law in a second. It's like this isn't, I mean, now that we know why this is true, it's not so surprising. It's just that you have, the only reason why you have uncertainty in part A of the system is because it's correlated to part B. So you have, that means you have to have the same amount of uncertainty in both parts. That makes sense. Uh-huh. Yeah, well, I haven't even, so let me just say how I'll apply it to a condensed matter system. So far, it just could have any, it could just be like 5 particles over here, and see how they're entangled with 3 particles over here. Like I have, yeah.
So what I'm saying is that there is also part C here, which is
Oh, yeah, this has to be dividing the whole system. There can't be anything else besides A and B. It's not true if there's something else. Yeah, that's a good question.
Yeah, just return to the original question for all these
Yeah, this is, yes. So what it is, I can define fluctuations in the ground state to be the entropy of a part of the system. That depends on which part you choose. But for each part, you have a definition of fluctuations. And what the Schmidt decomposition proves is that that those fluctuations also correspond to entanglement. You can't have fluctuations without also having entanglement. So that's neat. Yeah. But if you take a part of the system, then it has fluctuations. So like I guess the usual way when you talk about 0-point motion or like ground state fluctuations, you'd say there's fluctuations because you measure a variable like the position of the atoms and you find that it's fluctuating. In this case, I'm not choosing a special variable. The only thing I'm doing is choosing a special region. And then I'm finding that that region has fluctuations. No matter what basis you look at, there's fluctuations. And the Schmidt basis is the one that has the minimum amount of fluctuations, but there's still fluctuations in that basis. So like, I just say, like one thing that it just kind of an interesting thing that you may come like read about if you read stuff about quantum information. Like you can talk about, like I've been saying, this entanglement is sort of like a correlation between the 2 parts of the system. And to make that more precise, you define this quantity of called the mutual information between part A and part B of the system, which is the entropy of part A plus the entropy of part B minus the total entropy. And why is that? Why do I call that? Oh, so if that's the information, and I plug in these values, then I just get 2s of A, because these 2 are equal, and there's no fluctuations in this part. So the entanglement is half of the information. So why do I call that the information that is shared between the 2 parts? And we can think of that example. Well, let me think of a different example, because I had enough about food for today. So let's imagine my roommate and I have two backpacks, a red one and a blue one. And each day, whoever gets up first just chooses one of them randomly, because they like variety. And so then you'll find that we always have the opposite color of backpack. So if I would look at, which means there's a perfect correlation between the two backpacks. And we can see that from this formula. Because the entropy of person A is log 2, because there's two possibilities for what color his backpack will be. And the entropy for person B is also log 2. And if you had two uncorrelated things, the total entropy would just be the sum of the two entropies, because they're uncorrelated and it would cancel out. But but in the case of the backpack, there's only two possibilities. If one's red, the other's blue, and vice versa. So this is also log 2. So there's less information, there's less entropy in the combination than you would expect if there were no correlations. And that means that there are correlations. So by subtracting that out, you can see how much correlations there are between the two people. So that's why that's called the classical, that's called the mutual information. It would be log of 2, because the two possibilities are red for person 1 and blue for person 2. Yeah, like in principle there's 4 possibilities, but these each have 50% chance. So then you get log of 2. So the idea, that's the idea of this, is the only way you make it. So when you talk about information, you talk about a system where there's a little bit of uncertainty, and then the uncertainty is correlated between the different parts of the system. So that's what this is saying. Or not the original basis, but even this best basis. Like if you try to find a basis that factors, where an unentangled basis, there's some uncertainty. The only way you can get rid of uncertainty is by taking an entangled state. But if you want to define the part A and part B as separate states, it's not possible to avoid an uncertainty. Where you're saying where this is, where what's not zero?
Well, non-trivially high.
Oh, where it's zero? Any time you have independent random variables, this comes out to be 0. And I think that's the only, I don't know if that's the only, I think that's the only time it can be 0. So like if we had in our house an infinite supply of backpacks, then yeah. So an interesting, a very not very interesting sounding theorem, but it's actually mathematically very hard to prove, is that this is always positive, or greater than or equal to 0. So I mean, if that really is the information, it better be positive, because knowing something about B shouldn't make you less informed about A. But it's actually not an obvious fact. And the reason why it's not, in classical systems it's pretty obvious, but in a quantum system things are weird. So one way you can see that a quantum system is weird is that you'd expect a bigger system to have a bigger entropy. Right? If you have more variables, there should be more entropy in it. But we already saw that's not true in a quantum system, because this can be 0 and this is non-zero. And that's because in the quantum system, these are sort of defined with respect to different bases. This is defined with respect to just like the basis of the ground state and everything else, which it's not, all the states that it's not in. And this is defined in this other basis.
Crazy situations where information can be.
Yeah, it's not. This is violated in a quantum system, but this one is true in a quantum system. And there's actually an even more complicated thing called the conditional mutual information, which is something like intuitively, it's like if you measured C, it can change the information that A tells you about B. And it's defined as this. And this is actually also always greater than or equal to 0. And that, if we might be using that tomorrow, if I get to it. This is useful to understand topologically ordered states, this inequality. So now let's think about a system, like a metal with those Friedel oscillations or something, or it could be a magnet with some kind of fluctuations. Oh, this is always annoying because they draw a lot of stuff. So we just take a magnet with many spins in it. And then I'm going to apply these ideas by separating out a region A and call the rest of the system a region B. And then what I just showed is, like what the Schmidt decomposition stuff shows you, is that the system as a whole can be in a definite state, but part A of the system will then be in a mixed state, which is described by this density matrix. And if I look at this state, I could say that looks like a thermal ensemble. If only the Hamiltonian if I just saw the state and I didn't know how it happened to get that way, if somebody just pulls away the rest of the spins and I see these spins, I would say, oh, it must be at a finite temperature because it's not in a definite state. So then I'd figure out that. But I can figure out what the Hamiltonian is, because the Boltzmann distribution tells me that this probability is equal to e to the minus the energy over kt. So that means that the Hamiltonian, if this were right, that this were a thermal state, this Hamiltonian for this system would just have to be like this energies, ei times I. Or that's just kt times log of 1 over p. So for example, if I had a state like square root of 1/3 up times down up, if I have part A is a spin 1/2 and part B is a spin 1/2. Then the probabilities would be 1/3 and 2/3. And that means the energies would be like kt log 3 and kt log 3/2. So what I'm doing is I'm saying I can find a Hamiltonian that will simulate this probability distribution. And the reason that is a good partly why helps your intuition is that we're basically assigning states that are unlikely a high energy. So like this is unlikely, so we're assigning it a big energy, and this is more likely, so we're assigning it a small energy. And then we can use intuition from statistical mechanics.
So is this Hamiltonian directly to be local?
Yeah, so that's a good question. That's partly, yeah, that's what I'm going to talk about a little bit. Yeah, there's no way to figure out the temperature. If I just know, if I see a state, it could be either a low temperature and a Hamiltonian with weak interactions, or a high temperature and a Hamiltonian with strong interactions. Right, this KT cancels out in the density matrix. So that's a good question. So what I'm going to do, I'll just set KT equal to 1 from now on, because there's no way to know what T is. just by looking at a probability distribution, you can't figure out what the temperature is.
It's not always possible to
No, any probability distribution, I just take the logarithm of it. I call that the energy, and that'll be a Hamiltonian.
saying that.
Well, this is, I mean, let's see. I mean, I guess you'd find a Hamiltonian where it's thermal. It's just not it's not the real Hamiltonian. Oh, yeah. But also, this is looking at a part of the system anyway, like, because you're talking about a definite. Yeah. So I'm going to call that the Entanglement Hamiltonian, because it's a Hamiltonian that describes the entanglement of the system. And it's like, if you wanted, like from the beginning, where I said I want to look at a ground state and figure out something about the excited states, this is sort of an attempt at doing that, because I'm starting from the ground state and constructing a Hamiltonian. It's not the real Hamiltonian, but it's some Hamiltonian. And so maybe the excitations of that Hamiltonian could be related some way to the actual physical excitations. Because after all, like, the things that are more likely to happen, like in the ground state wave function, are the ones that have the lower energy. And that's kind of what like if you look at 0-point fluctuations, you expect the ones that are most likely to happen are the ones that don't have too much energy. Because from like second order perturbation theory, you'll have fluctuations. You'll have, like if you add in a perturbation, you'll mix in fluctuations that have, with the probability that goes as 1 over their energy. So how much is this like a Hamiltonian? Like, I mean, you can call anything a Hamiltonian, but it might be very complicated because you take this log of this many-body density matrix. And it seemed like from some numerical calculations, and there's also some theoretical reasons, it seems like it's kind of similar to a real Hamiltonian. Like it actually involves mostly local interactions. Like there's longer range terms, but they decay exponentially. But there's one big difference, which is that if you have this region A and region B, the real Hamiltonian is kind of spread out over the whole system, but the entanglement Hamiltonian is localized around the boundary. So the entanglement Hamiltonian is one-dimensional less than the physical system.
And then it also depends on A, so you let A vary.
Yeah, for each, yeah, but there will be, let's fix an A. Yeah. Oh yeah, this is for a gap system. Yeah. Yes, that's a good point. I always forget to say that, actually. You'll see why in a second why I'm saying that. Yeah. So the reason is that the entanglement Hamiltonian, if let's just imagine we look at it, something like a band insulator and find the entanglement Hamiltonian, it turns out it'll look something like you'll take the bands of the original system, but you'll make their energies depend on space. So if you have like the bands, a band here and a band here, and there's a gap. Then as you move away from the boundary, x represents the distance from the boundary, the bands will go up like this and down like that.
That's because there's no entanglement entropy.
Yeah, because the chance of a fluctuation happening far away from the boundary gets smaller and smaller because
You're not entanglement.
because it's not entangled with the outside. It can a particle inside. I mean, it's translationally symmetric before you make this division. But so particles inside can fluctuate as much as particles anywhere, but they fluctuate within the system. So they don't create any entanglement. But particles near the boundary can move between the two sides, and that leads to fluctuations in that density matrix. So the most important fluctuations are the one near the boundary, which means those are assigned to low energy, and as you move away, the energy increases and increases.
But then what do you mean then by? So I end up in this picture, but why do you say like there's Hamiltonian everywhere? It's larger, away from the boundary.
Yeah. So this is actually a kind of vague sentence.
Low energy.
Yeah. So the real Hamiltonian is, I mean, it's an operator on this whole region, but the low energy degrees of freedom are trapped near the boundary. Yeah. So okay. So then okay. So I'll just say. Yeah, low energy of the entanglement Hamiltonian. So like one consequence of this that is sort of the original thing that people realize is that because it's that low energy in the entanglement sense, excitations are trapped near the boundary. The entropy of the system, which is actually the entanglement entropy, is proportional to the surface area. To the area of dividing region A from region B. So that's the behavior of a gap system. Well, the Hamiltonian is actually everywhere, but the low energy excitations are exponentially localized near the edge. Yeah. Like how? I don't know. I think it's basically the correlation length of the system, but I don't actually know that. I mean, also depend. It's really you want to know how the energy. As you increase the energy, the penetration depth of the states increases. So there's some kind of a law for how the penetration depth depends on the energy. Let me just say like how we can use this to understand excited states of different systems, and then that'll just be the end. So we found this area law for a gap system, and then gapless systems have long-range correlations, and that's reflected by the entropy being larger, because the entanglement Hamiltonian isn't localized near the surface anymore. So in a one-dimensional system, the entanglement entropy, if you have a segment of a length L, the entanglement entropy goes like alpha log L. And a neat fact is that that this alpha is related to something about excited states, which is that the specific heat is equal to alpha over Vf times the temperature, I think times pi or something like that. So there's a connection between entanglement entropy and an excited state property. And then in 2 dimensions, it's actually even for gapless systems, you have an area law like this. So for gapless systems, you don't really see something interesting, even in 2 dimensions. I mean, in 2 dimensions, you don't see something interesting, but you can see in a topological system. We see interesting things. So there's two types of topological systems. One is like a topological insulator. And for topological insulator, you see a neat thing, which is that you have the edge states, which is like topological insulators are basically usually defined by the properties of their edges. And like those are excitations. But if you have infinite volume, you feel like, how can you tell that something's a topological insulator if you don't see the edges? And it turns out that the entanglement Hamiltonian has the same edge states as the physical system. So that means I can just take the bulk of a topological insulator, and I can reconstruct the edge states by looking at the bulk. And another kind of topological system is like a topologically ordered system in the sense of having like a ground state degeneracy in anyons. The system with anyons. In that case, there's something called the topological entanglement entropy, which is the entropy of this region that is proportional to the surface, but there's like an additive constant. Actually, it's usually called gamma. There's a constant that's added to it that you can't associate with one part of the boundary or the other part. It's just like a global piece of entropy. So that's how you can recognize like things like quantum Hall. That fact that there's anyons in a system without actually creating the anyons. You just look at this entanglement entropy. Yes. Yeah, that's why I put a minus sign in front of it. Okay, I'm done. I don't know if there's. Thank you. Is there time to do questions? Yeah. In this, basically no. So like, also like if you have a gapped 1D system, the area law, like the area law would actually be just a constant law because the boundary is of a region in one dimension is just a constant size, and that constant doesn't have any meaning, but the coefficient of the logarithm happens to have a meaning. It's sort of like anything local doesn't have a meaning. It's kind of because you could always change the interactions so that things would become more correlated or less correlated. Yeah.
So for the entropy,
it's something that is not really related to the physical Hamiltonian because like there's no real relationship between like the dispersion of the entanglement Hamiltonian or that and like physical properties. And I don't really know, like I think the rate it grows has to do with the correlation length, but I don't know a formula for it actually. Yeah, I think so. Well, I'm going to talk about like how to actually calculate the entanglement Hamiltonian. And like for relativistic systems, it's actually always a linear function, it turns out. Yeah, it's like the details. Well, I'm not sure. Yeah. Yeah. Okay. I think it's actually the other way around. It's the interactions along the boundary are local in the entanglement Hamiltonian, and I'm not sure whether they're local or not away from the boundary. Like it doesn't matter that much because as you go farther away from the boundary, the gap gets bigger and bigger. So you don't look at excitations far away from the boundary. Like there's an effective Hamiltonian that just uses spins along the boundary, and that one's local. But I don't know if it's local. If you took the exact entanglement Hamiltonian instead of the effective one, I don't know if the interactions are local or not, like in the perpendicular direction. No, none of that's rigorous. But for a relativistic system, you can actually calculate the entanglement Hamiltonian, and it's local. completely. And there's some simple, like things with two bands, you can figure it out analytically, and it's also local. But I think those are all special cases, so I don't know what actually happens. Yeah, you have to have conformal symmetry, actually. Yeah, this is for conformal. If there's conformal symmetry of the gapless point. And this alpha is usually called the central charge divided by 3. And it's a rational number, which is fun. Yeah? Or so alpha you can get from the entanglement, but yeah, you couldn't get VF. I don't know why I called it VF actually. You can't get this V from the from the entropy, because it's just sort of this, like, you can take any Hamiltonian and if you multiply it by 2, then everything happens twice as fast, but the ground state stays the same. So you can't figure out the speed just by looking at the ground state. Yeah.
If I bipartite my system in a Jacob pattern or something like that,
I don't know. I haven't really thought about things like that. Yeah. Oh, well, people look at like entanglement between different segments, and you can get, like in a conformal theory, if you take one segment, you can find the central charge, and that's all you can find. But if you take 2 segments, Carty showed that you can get like everything about the conformal field theory is actually contained in the entanglement. As if, or yeah. So, and you can, in higher dimensions, you can look at entanglement around corners, and that tells you some information too.
so to construct the
Mm-hmm.
so is there other
You mean like, is there another? That's the definition of it, is what I wrote. Like that. But there's like a more efficient way to calculate it then. You don't have to find the, like this sounds very hard because you have to take a Schmidt decomposition of an exponentially big state. And like, hopefully there's an easier way to do it. Which, for a relativistic system, there actually is an easier way to do it. And the other thing is, if you have a one-dimensional system which you solve by DMRG, you automatically get the density matrix. So this definition is actually really fast if you have solved something by DMRG. That's kind of why I got involved with this, is because my friend was doing DMRG and he gets all the entanglement spectra, like all the sets of eigenvalues of the Schmidt decomposition. And then you look at them and they're not just ugly numbers, like they have all kinds of patterns in them. And so that's something you can try to learn something from. Okay, I guess we could go eat dinner.
Can I continue on the question?
Yeah.
So if I have like the checkerboard pattern,
Uh-huh.
if I bipartite my system like this,
Uh-huh.
then I compute the entanglement Hamiltonian.
Uh-huh.
Do it have any locality properties? Do you expect that it will have any locality properties?
Oh, you mean like between the different segments or
Yeah, so
something?
if I trace out the shaded parts,
Yeah.
I would have an entanglement Hamiltonian that operates on just
Yeah, actually, Team Share has a paper. Team Share, a KTB postdoc. So it's all known, 1D, 2D.
So do you know if the locality?
So this will give you the phase transition if you stack, like this is SPT phase, you trace out a region, checkerboard region in an SPT phase that gives you the SPT to trivial transition. The entanglement spectrum will be the critical point.
But do you know what the locality is? Whether the operators are still localized? Low energy. What is the statement of the Hamiltonian, low energy Hamiltonian is d minus 1 dimensional? How does that translate?
Yeah, I guess if they're big enough regions, I guess you'd have stuff around the edge of each region. And maybe I think they would still only be coupled to nearby. Like,
So it would just be points.
yeah, in this case it would just be points and it would be like not nearest neighbors, but like short range coupling. Yeah.
So if I change this, they might start interacting.
If you what?
If I reduce the size of what I trace out.
Well then there's no like bulk and I think it would still be a short range interaction between the different segments.
But the edge can talk to each other.
Maybe just to repeat what you said. You said for topological insulators and the entanglement Hamiltonian also have the edge state. Are
Yeah.
you saying it's exactly the same edge states of the same spectrum with the actual?
They have the same, like whatever's topological about them, they also have that.
Okay,
But the dispersion doesn't have to be the same. Like the slope can be different.
I see.
It's not
the
even the same
parallelity
unit.
has to be the same, for
Yeah.
example.
Like it's not even the same units because the entanglement Hamiltonian is dimensionless and the physical Hamiltonian.